Geothermal heat and energy. Here's some videos just to kind of get some visuals of what's going on. So this is the origins of how the Earth was kind of created and originally gained all of its heat and energy.
On the Earth. Though that is indeed where a great deal of the heat in the Earth came from. Before the Earth was formed, it was basically an asteroid belt, but eventually enough mass ended up in one place that it started drawing all of those asteroids together. This was a pretty violent process. Every gigantic asteroid that got sucked into the Earth added massive amounts of energy to the system. The energy of those collisions and the friction between those bodies liquefied the Earth. The entire thing was a ball of lava. That is why it and every other planet is nearly spherical. In a gravity-neutral environment, liquids form spheres. Amazingly, after 4.5 billion years, some of that energy is still around. The Earth has cooled off, of course, forming a thin, delicious crust, but much of that heat is still there. And yet, we haven't really even started yet. There are two other important sources of heat. One is the transport of heavier elements to the center of the Earth. This also caused by gravity. That resulted in a tremendous amount of frictional heating. This appears to mostly be at a steady state now, but early in the Earth's history, it was a major source of heat. And then we have a major contributor that continues to heat the Earth to this day: nuclear decay. Certain isotopes of elements are unstable. We call them radioactive because they have a time limit, and once their time is up, they decay into other isotopes and elements, and in the process, they release energy. The largest contributors to this heating are uranium, thorium, and potassium. Now, we're not sure how much of the Earth's heat comes from each of these sources. Our best guess is that about 50% of the Earth's heat comes from radioactive decay, while the rest is left over from the process of planetary accretion. So, the Earth is, in fact, cooling, radiating about 40 terawatts of heat, while radioactive decay only produces 20 to 30 terawatts. But the energy content of the planet is so massive, and the crust forms such a nice layer of insulation, that we remain an extremely hot ball of mostly magma that we can occasionally use to generate power for ourselves. And no, it doesn't have anything to do with pressure. Thanks for watching this episode of SciShow.
Alright, and here's just kind of a more in-depth version of, geothermal heat in the Earth today.
Have relaxed in a natural hot springs pool, or seen the old faithful geyser blasting hot water into the air in Yellowstone National Park. But have you ever thought of where all that heat comes from? Well, it comes from deep beneath the surface of the Earth, and it's called geothermal energy. And we can use it to generate clean, renewable electricity. Okay, here's how geothermal works. Heat from the Earth's crust warms water that has seeped into underground reservoirs. In some places, when water becomes hot enough, it can break through the Earth's surface as steam or hot water. This usually happens where the Earth's crust, or plates, meet and shift. In the past, taking advantage of geothermal energy was limited to areas where hot water flowed near the surface. But as geothermal technologies advance, we can leverage even more of these natural, renewable energy sources. Engineers have developed a few different ways to produce power from geothermal wells drilled into the ground. Have a look at this. It's a dry steam geothermal power plant, and it's the most common type of geothermal technology used today. Underground steam flows directly to a turbine to drive a generator that produces electricity. Pretty straightforward. Another geothermal technology is called a flash steam power plant. A pump pushes hot fluid into a tank at the surface, where it cools. As it cools, the fluid flashes, or quickly turns into vapor. The vapor then drives a turbine and powers a generator. A binary cycle plant works differently. It uses two types of fluid. Hot fluid from underground heats a second fluid, called a heat transfer fluid, in a giant heat exchanger. The second fluid has a much lower boiling point than the first fluid, and so it flashes into vapor at a lower temperature. When the second fluid flashes, it spins a turbine that drives a generator. The environmental benefits of this clean, round-the-clock, renewable energy source are substantial. Low emissions, small physical footprint, and minimal environmental impact. The few byproducts that can come up are often re-injected underground. Geothermal energy can also help recycle wastewater. In California, wastewater from the city of Santa Rosa is injected into the ground to generate more geothermal energy. Some plants do produce solid waste, but that solid waste may contain minerals that we can remove.
All right, I'm sure other lectures are going to go into more depth about the energy systems. Here's just a quick view.
Up is boiling hot springs, and
quick view of Iceland, which is kind of the epicenter for geothermal energy. You can see just all around them the it's steaming. It's not smoke or anything, but you know there's visible water boiling off, the mud's bubbling. You can see it's just a lot of geothermal action and activity going on. As you can see. All right, so going forward, just some things to think about would be what is the average heat flow on the surface of the Earth? What geological regions are likely to have high heat flows? And where on Earth does the highest heat flow occur? And where is geothermal likely to be developed in the future for power generation? And specifically, where in the United States? Origins of Earth's heat. So the video touched on this a little bit, but the Earth was created over 4.5 billion years ago, and it was basically, there was a cloud of particles called the solar nebula, and it was composed of a variety of minerals that make up on the Earth today and rocks, including some native metals, frozen volatiles like water and hydrocarbons. And all these particles, they're just dust floating around, and they would collide with each other, and these collisions caused a lot of energy, and as the particles got bigger and bigger, they got clumped together and eventually formed different planets. And all these collisions turned kinetic energy into heat energy. Along with metals and rock particles, the Earth is also comprised of an abundance of radioactive elements. These elements have a relatively short half-life, which leaves them to decay over time. And as these radioactive elements decay, the atoms that they release turn into kinetic energy, and they interact with the atoms around them, and this energy is transformed into heat, which is another major contributor to increasing the temperature of the Earth. So all these processes put together, the Earth basically turned into a spherical planet of liquid magma, and just as well as all the other planets in our solar system were just liquid hot magma floating through space around the sun. And as it began to cool, the heavier, more dense liquids congregated towards the middle, which is why the center of the Earth is comprised of iron. And when it was in a liquid state, it could flow, these heavier metals could flow freely, which gives you the reasons for the segregated layers that we find on our planet today. And here's just a cutout of the Earth. Here's the inner core, the outer core, mantle, upper mantle, and of course where we live, the crust and the atmosphere. So today, approximately 6% of the heat comes from radioactive decay. So the Earth is cooling, but they're still generating heat from decaying radioactive elements. And here is a volcano, which is just an obvious site of how the Earth contains a lot of heat energy. Okay, so as the Earth began to cool and this nice crust layer that we live on today became solid and livable, plates began to form. And as everyone's familiar with tectonic plates, they are floating on a layer of liquid magma, which allows them to move around freely at a very slow rate, but in fact they are constantly moving and shifting all the time. Here this shows the heat flow on Earth, and as you can see, the plate boundaries is where there's a significant amount of heat flow from the center of the Earth. Here's a close-up of some plate boundaries. So here's two spreading plates. These would be on oceanic plates, and as you can see, as one plate goes left, the other one goes right. It causes magma to be forced up through the middle, and in the areas like this, there's a large amount of heat flow. Here would be two plates coming together, and as one plate goes on top of the other one, there's a significant amount of friction forces, which creates a lot of energy and a lot of geothermal activity. That's where you find volcanoes and things in that nature. Here's a rift zone, which is similar to the spreading here, but this would be on a continental plate like the Great Rift Valley in Africa. And same thing, as plates spread apart causes liquid magma to fill in the gap. Here's a close-up of a subduction plate. See, there's this plate moving to the right, this one moving left, and it causes one to go under the other. And the grinding between the two plates causes a lot of energy. This is where you find volcanoes, also where you find lots and lots of earthquakes. And this friction creates liquid magma, which creates higher pressure, and it's released through volcanoes or other things like that. The structures of plate boundaries are spreading, subduction, convergence zones, and transform faults. All these have high activity for geothermal potential, and is also where you find significant amount of earthquakes. So here we have an extensional environment. So right here, this plate is moving to the left, this one to the right, causes magma to rise up and fill the void in the middle. These are most common on oceanic crust. Compressional environments, these are subduction zones, one plate going over the other. You'll find volcanoes and mountains forming here, but this oceanic plate, for example, is sliding under this continental plate, which causes magma to heat up and rise to the surface of the earth. This is a very common area for geothermal power generation as well as earthquakes. And then the third main type of fault would be a transform fault, and that's where the one plate is sliding against the other one laterally. So they're not going into each other or away from each other, but they're slipping against each other, also called a strike-slip boundary. Here would be these are hot spots, which are geothermal areas where there's liquid magma pouring right onto the surface of the earth. This here is in Hawaii, which is pretty famous for this. Obviously, the Hawaiian Islands are very volcanic, and here is Iceland, and you can see that there's this constant magma flowing through the surface of the earth. Some tourists may be getting a little too close. Heat transfer on Earth occurs in three different ways, either by radiation, where heat is transferred radioactively by the emission or absorption of thermal photons, or conductively, where heat is transferred through direct physical contact, or convection, transfer of heat from one place to another by the movement of fluids. So conductive systems. Heat is conducted over the entire surface of the Earth from the center upward to the ground surface. By measuring the heat capacity of certain materials, different kinds of rocks like granite, basalt, etc., and by knowing the temperature at one depth and another depth, you can calculate how much heat in watts is flowing through an area. This is useful so you can determine the heat capacity of a particular location. So looking forward into some more conductive systems would be groundwater basins. So this is a source of geothermal energy from aquifers that are so deep that their temperature is raised by the normal geothermal temperature gradient. This mechanism of heating the water as such a system is then simply vertically conduction of heat through the crust. The fluid flow in the aquifer must be sufficiently slow that there is time for the water to be heated by this normal temperature gradient. If the water is moving too fast, then it won't have enough time to heat up. In some large groundwater basins, a fraction of the water circulates back up to the surface. That's when you can see, like for example, a hot spring. You can see that this water is heated and eventually makes it up to the surface. Here's an example. This is kind of a simple heat transfer question, but this has an application for geothermal energy. So if you had a heat flow through 100 meters of granite with a surface temperature of 25 degrees Celsius and a subsurface temperature of 100 Celsius, how much heat in watts would be flowing. So useful equation that might be a little familiar. You have the heat flow is equal to conductivity by change in temperature over a distance. Thermal conductivity of granite at 100 degrees Celsius is 2.43 watts per meter Kelvin. Change in temperature is 75 degrees. You don't need to put it into Kelvin, obviously, because it's just taking the difference. And plug it into the equation, and you get 1.82 watts. All right, now moving on to convective systems. Convective systems are geothermal systems with high temperatures and surface activity. At the present time, all major geothermal power stations operate on convective systems. In contrast to conductive systems, in convective systems, there's a flow of hot fluid through the system that determines the temperature and fluid distribution. In low temperature systems, the reservoir fluid is always water, while in higher temperature systems, steam can also be present. These geothermal reservoirs are divided into two types: water-dominated reservoirs or vapor-dominated reservoirs, depending on the phase of the system. And this is always depending on temperature and pressure, which will change the state of the fluid. So here's a diagram. As you can see, here's as you go deeper and temperature increases, the water starts to boil. So the deeper you are and the higher the temperature, the more likely to find a vapor-dominated system, whereas shallower, less hot system will be liquid-dominated. And here, so you have the magma, which is also flowing and conducting, and that heats up the water, and as water heats up, goes to the surface, we'll find hot springs or geysers, and then it spreads out, cools, and flows down through a highly permeable area and heats up again, and it just keeps going in a cycle. This flow of fluids is what keeps these systems going. As the hot fluid comes up, cools down, and then flows back down, heats back up, cools back down. Here's a hot springs in Iceland. And here's one in Steamboat Springs, and this is relevant because this is when they first started studying convective systems in the United States. So liquid-dominated convective systems. These are systems that require a large amount of heat compared to the normal temperature gradient, and they're found in regions of recent volcanisms. So usually on plate boundaries and areas with a lot of geothermal activity. Circulating water makes close contact with magma, and this heats up the water, causes it to rise. But the magma itself is also convecting, because if it's not circulating, it's not going to maintain its heat. So it's convecting as well, deeper in the earth. The pressure drive that sustains this hot recharge of upflow and downflow is the buoyancy difference between the columns of descending cold and hot fluid. Like I mentioned here, hot fluid, the buoyancy forces it up, cools down, comes back down. So moving on to vapor-dominated convective systems. These are similar to liquid-dominated systems, but they contain superheated water as steam. These reservoirs contain a static column of steam, and any associated surface activity will be steam-related, like geysers, stuff like that. Or like what you saw in the video in Iceland, the steam just escaping from a random point on the Earth. Stream spreads laterally throughout the reservoir, and as it spreads, it loses heat. Some of the steam condenses, absorbs the gas, and then migrates down through gravity, because it will be more dense than the steam. In steam-dominated reservoir, the counterflow system of steam moving up and water moving down controls the fluid distribution. So the gaseous steam moves up, it cools down, condenses, and then flows downward through gravity, heats back up, and that's what keeps the flow distribution moving. Here's an example of some surface activity. This is in Yellowstone, a geyser everyone's probably seen, or at least seen pictures of geysers. In a vapor-dominated reservoir, the pressure increases slowly with depth, implying that there's a low low permeability boundary, which means it's a pretty sealed system on the sides, bottom, and top. There's going to be low permeability, which is not going to let water or gas escape, and that's what keeps the high pressure and steam and this fluid flow working. Of course, it's not going to be sealed. On a geyser like this would be a natural discharge of a vapor-dominated system. So moving on, reservoir evolution. As we exploit these geothermal areas, whether it be conductive, convective, etc. You're changing the natural structure of the well by the system by extracting this heat, whether you're taking it out and not replacing it, or somehow you're going to be affecting the well. So in high temperature geothermal reservoirs, a decline in pressure caused by exploitation may initiate boiling in part or all of the reservoir. In this case, the changes of the reservoir caused by exploitation will include changes to the steam-water ratio as well as pressure and temperature changes. So this is something that needs to be considered when trying to exploit a geothermal system. So this little diagram here, as you extract boiling steam or water, you need to generally inject cool fluid back into it to artificially continue the flow process. So as you take hot water in, put in cold water, then it can heat up, and then you can keep the cycle moving in an ideal case. So for my case study, I wanted to include Iceland. Iceland sits directly on a spreading center in the mid-Atlantic ridge and is a hotspot for geothermal activity. Iceland has the greatest per capita use of geothermal energy in the world. In 2006, 26% of electricity was produced from geothermal electric generators. In addition, hot water from power plants and geothermal resources account for 87% of the hot water usage in the country. So here's just some pictures of geothermal production in Iceland. So to sum things up, the Earth was formed over 4.5 billion years ago from billions of dust particles, including rock, radioactive material, and water. And these particles collided with each other, and these collisions and kinetic energy turned into heat energy, along with the radioactive decay caused the planet to become so hot it turned it into a liquid form. The denser material went to the center of the Earth, and the lighter material expanded to the outer layers of the Earth, and this created the different layers that we have today, including the crust that we live on. And on the crust, there were tectonic plates that formed, and these are relevant to geothermal energy because these are where all the hot spots and geothermal sites are located. Heat is transferred on Earth in three ways: through conductivity, convection, and radiation. Convection is just the normal heat gradient, the center of the Earth heating outward, and this is factors that contribute to this would be conductivity of material, whether what material it's going through, whether it be granite, basalt, etc. Convection is the transfer of heat by movement of fluids, and this occurs when magma is circulating, heating up water, flowing water, which then circulates to the Earth's surface. You get things like geysers, hot springs, stuff like that. I would say the main thing to take away from this is just the origin of heat flow in geothermal systems. Hot fluid heats up deep in the Earth, raises to the surface, spreads out, cools down, comes back down, heats up again, cools back down, heats up again. This cycle is what drives the flow of heat transfer in regards to geothermal capability. Thanks for listening. Let me know if you have any questions.